One of the hardest set operations is often to prove that two sets are disjoint from each other, that they don't share anything with each other, because you have to prove that there is nothing that they have in common, which is a pretty exhaustive operation. And this is useful, though, to be able to see that sets are disjoint, to represent equivalences and to test whether things are connected. For example, if you know about some networks, you might want to know, do they connect? Is there a way to get from this network to that network? Or is there not? Are there two areas that are connected on a map, or are they not? So that if someone wanted to travel from Puerto Rico to New Hampshire, we would want to be able to easily discover that there are not roads that connect those two places. So, for example, going over water versus open land versus there being a forest or a mountain in the way, or things like that. Navigating mazes. The problem is made harder because we often only know local connectivity information. We don't know usually about the bigger picture. We have to look at each individual road and find the route there if we're looking at a map to prove that two places are connected. We'll look at the data type of a disjoint set that's built specifically to be useful for this kind of operation. Because the naive approach of this operation would be to take every item from each set and do a full pairwise comparison. Is this item from set 1 in set 2, which requires searching all the way through set 2 to prove it's not? Is this second item from set 1 in set 2, which again would require searching all the way through set 2? That's a very expensive operation to do. We need better ways. If you recall some operations that sets might do, a union is to take the items from two different sets and combine them into one set without duplicating anything, of course, because a set is not allowed to have a duplicate. An intersection is finding the items that they share, and the new terminology that we'll deal with are specifically disjoint sets. These are two sets A and B, and they are disjoint if they have no element in common, or in other words, if their intersection is empty. We can view a disjoint set like a graph problem, where we were trying to see if two nodes are connected in a graph. So if we had a set of nodes and a set of edges, which are represented as pairwise connections from node 3 to node 5, from node 4 to node 2, and so on, then we could ask some questions about those. If I have X and Y, are they connected? Can I step from X to somewhere to somewhere to somewhere and get to Y? And we could tell that kind of thing based on the edges in that graph. And how many connected components are there in that graph? Is everyone connected to everyone else, or are there disjoint pieces of that graph that don't actually connect to each other? And the connected components in this can be viewed as equivalence classes, like those separate networks, separated land areas, and so on. So to answer these kinds of questions, we'll use the abstract data type of a disjoint set. You can efficiently answer questions like this without having to do the full pairwise comparison, and we'll see how. Our data will be a collection of possibly mutually disjoint sets, at least one set, and if we have multiples, they would be disjoint. Our operations would be to be able to do the union on two sets, but the interesting thing about a disjoint set is that we will identify it by one of its values. So we're doing the union of the set that contains U and the set that contains V. We refer to the items like those points X and Y in our graph, and we would say we could do the union of the set that contains X and the union of the set that contains Y, because we don't know yet whether those are the same set or not until we've done the evaluation. A find operation, and this is almost sort of a reverse lookup. We do a find on an item in the set, an element in the set, and it returns us the identifier for that set. It returns us something that identifies the whole set. And then the make set operation creates a new set only containing one value that we've given to it. To show some conventions for this, we will choose one of the members of each set to refer to as its name, as its identifier. It does not really matter which one for our purposes here. There may be better or worse ones that you could choose as the identifier, but that will be the one that's sort of we use to refer to that set. So if it were important somehow or that sort of thing, then we might choose it. But really, ultimately, for our purposes, we could choose any one of the items. It's useful because now we have a way to refer to the set. This set doesn't really have a name. So we pick an item in it and we call it the 5 set, or the 8 set, or the 9 set, or the 1 set. And all that really means is this set contains 5 and some other stuff maybe. So that find on an element returns the name of the set that contains that element. If I ask to find 3, it returns that 3 is in the 5 set. And if I ask to find 4, it returns that 4 is in the 8 set. And then our union operation merges the two sets into one. So that if I said, give me the union of the set that contains 5 and the set that contains 6, 5 happens to be the identifier from that set, and 6 happens to be one that was not the identifier, so I would find the identifier and I would merge those sets. And you'll notice, by the way, that this disjoint set abstract data type contains all of these different sets here so that we could have all of the networks that we know about. And then we'd be able to test our elements in the 5 set, or our elements in the set that contains 3, also in the set that contains 4. Well, we know they're not looking at our data structure, but we maintain all of the disjoint sets that we know about, and then we're able to answer those kinds of questions. So we have now a common operation sequence on all of these sets that allows us to tell if things are connected or not. If we call find X and we get a different result than find Y, then we know that they are not connected, X and Y. We could do the union of the two sets to try to merge them and make connections. So to find connected components, we start with an empty disjoint set, S. We populate S with some sets of singleton sets of vertices with the cardinality of as many vertices as we know of, as we have. We call union using vertices that are indicated in those graph edges, so that if 3 and 5 are stated that they're connected, then we merge those two sets by calling union on them. If, for example, let's say 4 and 2 said they were connected, then we would merge those. But if we had more connections, like if it also said that 8 and 7 were connected, we might merge this set that contains 3 and 7 and the set that contains 8 and 1. So our edges would implicitly have us merging multiples of these. And so we would say, when we see an edge, we would take one end of that edge and the other end of that edge. We would say if those are not already in the same set, do a union of their two sets. The resulting disjoint set indicates the number and makeup of the connected components. So we might have some groups that were clustered into one set and therefore were all connected as a subgraph. And then we might still have one or more other disconnected subgraphs within there. And that's fine. That will then allow us to ask questions about what is connected and what is not. So let's look at the implementation of how we actually do this, because this is a bit bizarre. This weird reverse lookup where I take an item and I find the set. How do I actually even do that? So we use something called an up tree, which is a tree in which all we store for any node is its parent. And we keep a forest of these, in other words, multiple trees that will maybe be disjoint from each other. So all of these trees displayed here could belong to the same disjoint set. It would have all of them. And so if I went to look up 2, I would find that it belongs to the 0 set. And if I went to look up 3, I would find it also belongs to the 0 set, and I would know they are connected. But if I looked up 5 and 2, I would find 2 belongs to the 0 set, and 5 belongs to the 4 set. They are not connected. So in these up trees, each node has only a parent pointer. The root has a parent pointer to itself so that we can tell it's the root. And every disjoint set in our disjoint set abstract data type is its own up tree with its own root as its representative member. To implement the find, if we can get to the element, if we already have the element, then we can just jump up to the root and that tells us the identifier. But we don't yet know how we're going to be able to grab the elements. So hold on to that thought. I know it's confusing for a moment because we're used to coming to the root and navigating downward to find things. Assume we can grab the elements in it and that those elements have parent pointers, and we'll be able to check what the parent is, what the identifier is for that set. And to implement union, we just take one of the parents for one of the sets we're trying to do union on, and we make the parent of the other tree its parent. So here we did the union of the 0 set and the 4 set. We took 4 and made it the child of 0, or made its parent 0. So now it's a part of that up tree. And if I asked for 5 and 2 to see whether they were connected, now they both would have 0 as their identifier for their set's identifier. When we do union, we want to do union by rank, meaning each node has a rank associated with it, the height of its subtree. And when we do the unions, we want to make the root of the smaller rank tree point to the root of the larger rank tree, like we just did a moment ago. The 4 tree was shorter, so we made it go under the 0 tree, because we want to maintain shorter trees just like we always have. It's best if we can keep our trees short and therefore do quick navigation through them. These are, by the way, not binary trees. They're allowed to have as many children as you want. And in fact, it will be better for us if they do, because we want that O of log n time for operations in them. So in addition, as we do find on a path, we will compress that path, because essentially we're not asking for the route from X to Y. We are asking whether X and Y are connected. And if that's the only question we're answering, then we don't need to know that to get from X to Y, you have to go through A, B, and C. We simply need to know that X is in the same set as Y. And so when we find the paths to the root, we'll just go ahead and move everybody closer to the root, directly connect them to the root, so that if I ask questions about them again later, I will instantly be able to find out that they are in the zero tree, for example. This shortens your tree as you go. Every time you do a find, you're improving the performance of your tree, and it only costs O of log n because the lookup was O of log n, and all we're doing is we're just changing those connections as we do the lookup. Once we find the root, we can just hook everybody in to that root that we saw along the path. So for example, if I did a find of 5 in this tree, then when I find that 5 connects to 0, I may as well just connect 5 directly to 0. So next time someone asks, I'll be able to just say, yep, 5 is in the 0 tree. Only one step. This prevents us from getting very long branches in the tree here. And then if I did a find of 9, I could continue doing the same thing, that 9 could connect to the root and 5 could connect to the root when I'm done. Of course, I would have had to have navigated up to the root, so this will require log n storage as well to remember I saw 9, I saw 5. When I'm done, I really ought to connect them directly to the root so that the next time if someone asks if 9 and 5 are connected to each other, I'll know they're both in the 0 tree, and it makes it much quicker. For the implementation, you actually can store this whole forest of up trees in a map. For example, we could look up the parents of every node in each of these trees, and we'll see that the parent of E is B, the parent of D is A, the parent of A is itself, so we could recognize that it's a root, and so on. So this is just one of the up trees represented here, but there's no reason I couldn't have a map that tells the parents for each of these, sort of like I could use a map that tells the edges in a graph. So each of them will have only one parent. There may be multiple children, but that's okay. I'm only looking up the values of the parents here. So then that allows me finally to understand, I hope, or allows you finally to understand that when I ask those questions like what set does E belong to, I'm looking it up in a map, and I'm looking up E's parent, and then I look up the parent of that until the parent of whatever I have is equal to itself, and I recognize that I have a root. So that's my find process. Look it up in a map that holds all of my nodes, which is only O of n storage there. And when I do those lookups, then I'll just keep looking up until I find something that points to itself in my map. And that will allow me to do quick lookups. I do a lookup in the map of E. That tells me its parent is B, tells me its parent is A, which then tells me its parent is A, and I've found that E belongs to the A tree. And if I do a lookup of I, I'll find its parent is H, and that its parent continues to be H, and so I can see that E and I are in separate trees in this forest of up trees, meaning that E and I are not connected in my set, my disjoint set here. We can store the ranks separately so that we can do those evaluations when we're merging two trees. I could store the rank of those in a separate map, so I could look up rank of C or rank of F or rank of H, those heights that'll help me in my union operation. Just a separate map for that. Okay, so it's 2n for my storage if I need those ranks. Still not a huge deal for very quick lookup and very quick operation of disjointness, of telling the two things are not connected, which could be an O of n squared operation, to go through every item and find in one set and find that it is not in the other set. Could be O of n squared. We've now narrowed that down to an O of log n operation by storing things with these parent connections that allow us to find the identifier for those subsets, those disjoint pieces of sets. Here's the actual implementation of each of those different operations. If I want to make a set, I set the parent of the item that I've been given to itself, and I set its depth, its rank, to 0. If I want to find, I say if I'm not at an element that is its own parent, then I just do the parent of the element that I'm at. So I'm going to be sort of recursively finding the item, or from the element that I was given, the X, find its parent, find that one's parent, find that one's parent, and when the thing has itself, when the element has itself as a parent, I return that element. So the union, I do find set on the X element I was given and find set on the Y to get the roots, because what I want is the roots of those two sets. I can't just merge at any old location. I need to merge at the roots. So if those two are equal, then I'm doing the union of a set with itself. I can return, I'm done. The union of a set with itself is that original set. But if it's not the same set, then I take the one with the smaller depth and I make that be the child of the root of the set with the larger depth. Again, I want to maintain shorter trees, and I've just got an if-else, whether one of them, the X one, is larger depth or the Y one is larger depth. So these disjoint sets, again, they're a bit wacky. We're using a reverse lookup where you can give me an element and I can tell you which set it is in. I have to use a single value from that set as an identifier because the sets may not have names naturally. And when I do that, I'm able to perform these operations, answer these questions of disjointness, of whether two things are connected or not, in log n time, which is much faster than our naive implementations that we might have done in the past for this kind of thing. And we can even improve the tree a bit as we go through by hooking things directly to the root when we do a find operation.